Okay, perfect. So we're going to do a really quick introduction before we get started with our first keynote speaker. So thank you again, everyone, for joining us. For those who are not familiar with me, my name is Laura Montoya. I'm one of the founders of the LXAI Institute and LatinX and AI organization. We really appreciate you being here with us at this social for ICLR. This is our third official event at ICLR. The ICLR conference. So we're very excited to be hosting again alongside this conference for our community of Latinx and AI. And of course, our goal as an organization is to really grow and provide a platform for the community, for the global community of Latinx and AI professionals. You can see that throughout our mission here, where we try to bridge communities, academics, and industry, and of course, politicians as well, working to further AI innovation and resources for Latinx individuals globally. So we do that in many different ways. A lot of that is, of course, through hosting these types of sessions, socials, as well as full workshops at large AI and machine learning conferences, which otherwise you may not have been familiar with or may not have been able to attend in the past. We have been running this organization since January of 2018. And our org is comprised, of course, of members of the community in areas of AI in education, research, engineering, and social impact. So we really try to have very high representation of the community and, of course, many different industries together within the org. Some of the things that we do and try to provide the space for our members is by hosting our members directory through our app. If you're not familiar with our app yet, we do, obviously encourage you to join. You can see the public directory here at lxai.app/public directory, where those who have opted in to be displayed publicly in our directory, you will be able to see all of them. If you do sign up either as a member or as an ally, you would have access to all of the members within our community that have signed up through our app. We do have many more people who are involved with our community who are not on our app, but this is just a great resource to connect, to get in touch with all of the things, all the events and announcements and opportunities that we have going on as well in our community. So things like grants that are available, calls for papers to submit workshops, and also to our new journal, which we'll be announcing shortly, and many other ways to collaborate, opportunities for employment, and getting involved with our corporate partners as well. So for those partners, and also if you tend to host different events as well, this is a great way to find collaborators, mentors, speakers, and candidates to increase your network or hiring pipeline within the community. For us, as you can see, some of the other events that we have coming up in the near future, outside of ICLR, we also have CVPR. We recently hosted at EACL. We also have ICML, which is coming up very shortly, and we're also in the planning phase for ICCB and also NACLS. So if your interests lie within any area of AI or machine learning, including computer vision or machine learning, again, this is a great way to get involved. And then also do take advantage of our travel grant fund. If you need assistance in order to attend any of these conferences, that's one of our major initiatives and part of why we raise funding in order to be able to provide that for our members in our community. So if you ever need that at any point, just contact us or take advantage of the application when it's available through our social media channels or online. And then also, of course, a major program that we launched last year is our mentorship program. So we really wanted to provide another way to support our community members and the work that you're doing. I think I did notice some of the leads of our mentorship program are also on the call today, Pedro and one of our advisors as well, Matthias. The goal of this mentorship program, again, is to support your research and connect you to senior mentors within the community. So basically, the idea is you would choose your research area of specialization, really inform us about what you want to learn, what you want to research, and grow your expertise in. After completing that quick questionnaire and being matched with a senior member of our community, we will then have you do that connection through a virtual mentorship program. So basically, you just connect with that mentor for one time every month for about 3 or 4 months, depending on the length of time prior to a particular workshop that it is co-aligned with. And then throughout that time, we encourage you and the mentor to connect on all the ways in which you can improve your research. So there you can talk about your career aspirations, you can get feedback on your research, find different ways to improve that research. And then also, if you want to particularly present your research after you have incorporated that mentor feedback, we would encourage you to practice successful delivery of your findings, and of course, publish and present at our workshops or affiliated journals and so on. So again, this is a great opportunity for you to gain more support through the community and get involved, of course, with our corporate partners. We want to, of course, thank our annual sponsors who, make a lot of this work possible and who have been supporting us, many of them from the start of our organization. That includes Google Research, Facebook, Microsoft, Amazon, Apple, and Salesforce. So again, if you have an opportunity to connect with them at any of our research workshops or socials and so on. And there are several others also who are not currently annual sponsors, but who have sponsored us in the past, and we want to thank them as well for their support previously. So now, without further ado, I would like to take a moment to also introduce our collaborators for this particular workshop. So all of these socials and workshops are, of course, put together by members of the community. So we consider them chairs or organizers. Here, the chairs for this particular social included Sarah Iris Garcia, Dennis Nunez Fernandez, Javier Turek, Maria Luisa Santiago, or Lois, and myself. And I would allow for a moment for them to also introduce themselves if they would like, so that you can become familiar with them if you are not already, and to thank them for the effort that they have put in order to make this day, this social, and also tomorrow's social available. And then also just a quick note prior to that, if you were not aware that this is actually a 2-day social, so we are meeting today and we are also meeting tomorrow in the morning. We wanted to allow for people who may be on European time or Asia Pacific time to have an opportunity to connect as well with our members and with our community. So please join us for day 2 if you can, if you are available. So with that, I will pass it off to Sarah if she is available. Do you want to say hi and give a quick introduction?
Hello, everyone. My name is Sarah Iris Garcia. I am currently an adjunct lecturer at Universidad Mariano Galvez in Guatemala. I am going to be leading and facilitating the research roundtable. So everyone, if after this meeting, we can go to Gather Town and then you can find me there.
Thank you very much, Sarah. And you did have a little bit of feedback, but for those who didn't hear very clearly, you can please join Sarah for the roundtable on research. So here we have 3 topics. We have careers, internships, and research for the roundtables, and Sarah will be leading the research roundtable. So let's pass it off to our next chair for today. Dennis, if you're on the call, if you want to say hi and introduce yourself.
Yes, hi everyone. I'm glad to see you here in this event. My name is Dennis Nunez Fernandez. Currently, I am working at Universidad Peruana Cayetana Heredia as research assistant. I have previous experience in Poland and Italy doing some internships. So I will help you in the internship table, and I will contribute you with some internships, summer schools, and more interesting opportunities. Thanks.
Thank you very much, Dennis. And then we also have Javier Turek. Javier, would you like to introduce yourself?
Hi, everyone. My name is Javier Turek. I'm really glad to see all of you here. I'm originally from Argentina, and I'm a research scientist in machine learning at Intel Labs, and I'm currently in the United States. And later on in our networking session, I will be facilitating the career discussion and hope to see you all there.
Thank you very much, Javier. And Lois, did you want to introduce yourself as well?
Thank you, Laura. Hi, everyone. My name is Maria Luisa Santiago, but everyone knows me as Lois. So I'm the General Operations and Logistics Coordinator for LXAI and ICLR. I've been with the organization since August of last year. I take care of the general communications for LXAI. So if you need anything at all with the organization, you can reach out to me. Thank you.
Thank you very much, Lois. Okay, great. So I think with that, let's just do a quick overview of the schedule, and then we can start our first talk. So today, obviously, we've done our quick introductions. We will be kicking off with Soledad Villar for our first keynote speaker, and then we'll have a quick Q&A session. We'll have our second speaker, Alvaro Soto, and then another Q&A session that will be followed by an open networking and socialization, including the roundtable discussion. So in that time, we will be switching over to our Gather Town space, where we'll be hosting those roundtable discussions. You can be connected to Gather Town and Zoom simultaneously. We will have both spaces open simultaneously, but the conversations will be taking place within the Gather Town space during that portion of the social today. So please keep that in mind and make sure you are connected and do not have any technical difficulties. If you do have any technical difficulties with that session, you can please just message us here in the chat or via Rocket Chat or via email, however you need to get a hold of us to ensure you're able to join. After that, we'll do some quick closing remarks, and then hopefully we'll also see you tomorrow for day 2. I know it's early if you are on Pacific Standard Time as I am, but please do join us if you're available. And we'll be having 2 more really great talks tomorrow, as well as a mentoring hour hosted by one of our corporate partners, Google, where we'll also be conducting a research pitch session, which is very exciting for the first time with our organization. So with that, I'm going to hand it off to Javier. Again, he'll be giving a more thorough introduction for our keynote speakers. Thank you.
Thank you, Laura. So now it's my pleasure to introduce our first keynote speaker today, Soledad Villar. Soledad is an assistant professor in applied mathematics and statistics at Johns Hopkins University. Her research focuses on mathematical data science. In particular, she's interested in optimization algorithms arising from data applications and machine learning. She received her PhD in mathematics from the University of Texas at Austin in 2017. And after that, she was a postdoc at the Simons Institute in University of California, Berkeley, and the Center of Data Science and New York University. Her research is sponsored by NSF, the Simons Foundation, and EOR. Soledad is originally from Uruguay, where she is right now. Today, Soledad will present perspectives on graph neural networks. Please join me in welcoming Professor Soledad Villar. Thank you.
Thank you so much for the introduction and for the invitation to be here. Please let me know if there's any problem with the connection of the audio doesn't work very well at any point. Okay, so first, I guess that I guess that first I would like to acknowledge that many of us are in Latin America or have family in Latin America at these times, and these are very hard times in Latin America these days for the pandemic and other reasons. And I think that having this community and events like this to build communities is very important for us, like in a professional level, and also given that everyone is working from home right now and it's hard to make connections. I think this is like a very nice opportunity. So thank you for inviting me, and yeah. And so my talk today is going to be about some different perspectives that one can use to take a look at graph neural networks. Graph neural networks is a very large research area these days. There's a lot of things coming up in the area, And I just wanted to make a short summary, since it's just a 20-minute talk, about different points of views that people use to understand these objects, mostly from a theoretical point of view, since I work in theory. So, so there is this famous quote from Ron Kimmel that is in a paper by Michael Ladd that says that the task of attaching theory to deep learning is like a magic mirror where every researcher seems themselves reflected. And so they believe that I'm the person that is going to bring the theory to this object. I think that's a very nice theory, like very nice point of view. And I think it may apply to graph neural networks as well, though not in such like not as so generally as it happens in deep learning, but also graph neural networks can be seen from many different points of view. So today I'm going to discuss some point of view of seeing graph neural networks as a generalization of spectral methods, and in particular, the signal processing point of view, where one can see this graph neural network as a generalization of graph filters that people have studied in electrical engineering and signal processing in the past many years. Also, there's the more theoretical computer science perspective of looking at graph neural networks as message passing algorithms and different ways to design different message passing algorithms where each node sends messages to their neighbors according to some criterion, depending on like different ways of defining your architecture. These are the point of view that is more used in practice, and there's very nice libraries like DGL that implement these message passing algorithms, and like the more standard point of view for graph neural networks. These, if one doesn't take into consideration that you need to use more than just the graph, then it will happen that there is a limitation on the expressive power on these kind of architectures. So I'm going to mention like the expressivity as a theoretical issue that people study. And finally, another point of view that is more from the mathematical side is to see graph neural networks as objects, like classes of functions that satisfy certain symmetries, in particular the symmetry that one needs to take into consideration is that if I give you a graph by giving you the adjacency matrix of the graph, then I need this. If I compute a function of the graph, then that function needs to change accordingly if I relabel the nodes, like apply a permutation to the adjacency matrix of the graph. And so one way of defining these graph neural networks is as a composition of different layers, each of them having functions that are invariant or equivariant with respect to some group action. In particular, the group that people take into consideration is the permutation group acting by conjugation. So, so I came to graph neural networks because I was working in my PhD. I was working in something completely different. I was working on data algorithms for clustering and graph matching. So when I went to my postdoc at NYU, I talked to Joan Bruna, and he told me, why don't we use graph neural networks to solve your point cloud matching problem? So this is how I started thinking about it. So I'm going to introduce you like one motivating example for this problem. So the idea is that if we have 2 point clouds like these 2 point clouds that I have here, like this point cloud and that point cloud, and I want to find a permutation that sends the points in one space to the points in the other space, I can write that as a quadratic assignment problem. Imagine, just for simplicity, that both point clouds have the same number of points, and we have a distance between pairs of points in my manifold, which is this figure of this guy. And so what what I want to do is to find a permutation from the points in one manifold to the points on the other manifold, like that, from the indices from one point to the other one, so that it minimizes this discrepancy when I align these pairwise distances. In that way, you can write many problems. So for instance, one typical problem that one can write is a point cloud point cloud matching, which I told you were like these A and B's are the pairwise distances within points in the manifolds, but also you can think of it as graph matching, finding correspondences between two graphs so that most of the edges align. So this X would be like a permutation that does that. And in particular, one of the problems that one can write in this way is the graph isomorphism problem, which is to decide whether there exists a permutation that completely matches one graph to the other one. So given that the graph isomorphism is known to be a hard problem, or not really hard, but from like the point of view of like algorithmically, then we can expect that this is not a very easy problem. And another problem that you can write in these terms is the traveling salesman problem, where you can think of A to be a graph where you have the pairwise distances between all the points in your space, and then B, you can think of it as a cycle, and then you want to match the pairwise distances graph to the cycle, so that minimizing the sum of the distances. So this quadratic assignment problem is simply hard even to approximate it. So we don't hope to have algorithms that work in general, but in data science, we hope to have to be able to approximately solve these problems for most instances that we get that, well, hopefully. So the approach that we thought about was, okay, we can use the graph neural network, given a graph and the two input graphs. So we can use a graph neural network to learn an embedding for my graph, which is like an n by n matrix, to a feature space that is n by v, where each node is represented by a d-dimensional vector, and then with that, then if I have an embedding, the same embedding for the other graph, then the problem becomes not a quadratic assignment problem, but just an assignment problem, which can be solved much more easily. So then that's the approach that we consider, like just use a graph neural network to learn an embedding for my graph, and then do the matching in the embedding space and do that. So the perspective that we're looking at here is that this graph neural network will learn some sort of a spectral embedding of the graph that is consistent with the objective that we want to do, which is the matching. So I have a question in the chat saying that, is this related to the Earth movers, Wasserstein-Kantorowicz distance? And the answer is yes, but this is like the Gromov-Hausdorff version of that, which is quadratic instead of like just the one distance, like just like yeah. So it's a little bit more complicated, yeah. But there's the quadratic version of this of the problem, or a problem similar to what you mentioned, yes. Okay, so one way of thinking about this is with of these embeddings is like learning a good spectral method to embed my data in a lower dimension space. So how can I combine the operators associated to the graph to learn a good embedding? So we can think of it as unrolling a power method. So if I say, okay, I want to find the top eigenvector of this matrix, I can just do a power method in this form. And now the operator that I'm looking at is going to be a sum of m's, with these m's belong to this space. And now the sum of m's with some coefficients that I'm going to call theta m, m, b, that. And now the idea is that, okay, instead of finding the top eigenvector, I'm going to find an embedding to a higher dimensional space at, let's say, in dimension dt. So then what you do is, instead of considering that theta m is just a scalar, what you do is you say, okay, theta m is going to be a matrix that goes from dimension d, like that is of size dt times dt plus 1, where dt is the dimension of the embedding that you have at the layer t. So, and then the next thing that you can do is actually, instead of applying this power method as you apply the typical power method, you can change the theta m in each of the iterations of your power method. So in each of the layers of your neural network. So that's changing in that. And then you can, here. That means like changing the t means like at each layer of the neural network, you are changing maybe the coefficients of the matrix that you're multiplying by. So it's kind of like a generalization of the spectral method of a power method, where you can change the operators that you're multiplying at every layer, and this is very overparameterized. And you do that also because you want to have something that is overparameterized. And so something to take into consideration here is that these objects are of size dt times dt plus 1, where dt is the size of the embedding, or like the dimension of the embedding. So in particular, this is independent of the number of nodes. And this is something that you want in your design, because you don't want, you want to be able to train a graph neural network on graphs of size n and apply them to graphs of different sizes. So that's something that you need to take into consideration when you design these functions on graphs that are parameterized. And the other thing that is relevant is that this formulation is equivariant with respect to permutations, meaning that if I apply a permutation to my matrix, like apply a permutation to the rows and columns of my matrix, then I get the same permutation in the output of the network. And that's the relevant thing that we will use in order to learn like problems like matching problems, and learn how to find a permutation that sends one graph to the next. So I think this is the important thing of this definition, is that you can think of these graph neural networks as a generalization of spectral methods that is independent of the number of nodes, the number of parameters independent of the number of nodes of your graph, and the result is equivariant with respect to permutation. And we do that. I can show you some numerical examples with this specific problem of these graph alignments, where I generate random graphs, like G1 being an Erdos-Renyi graph with NP, and then G2 is a permutation of G1. And so that's for the first example. So in that case, you can see, okay, the graph neural networks actually perform very well in this specific problem, and also for the traveling salesman problem. But this is not state of the art. There are many methods that are much better than what I did, that have better performance. But just conceptually, this is a way of thinking about how you can use these graph neural networks to learn this optimization, like combinatorial optimization problems, right? So so that's one type of graph neural network, but this is not necessarily the most common type. I think that in general, you can think of the graph network as a function, as an input, as a graph given by the set of vertices, edges, and then these are the features, and this will have an important point, the graph, the node features and the edge features, and the output is going to be an embedding of the graph, which is, you can think of it, that each of the nodes of the graph gets embedded in dimension D. So, and the fundamental property is the equivariance with respect to permutation. So yeah, so basically that, I think I have it here. F theta of G, of pi G, is equal to pi F theta of G. That's the equivariance with respect to permutation. And this, and there are many types of graph neural networks, as I mentioned here, and these are some of the references. Let me, I'm gonna just give you the most common formulation for these graph neural networks, which is the message passing neural networks. So how much time do I have left? I think we started a little late, so I think I have 10 minutes. Is that okay?
Yes, that's fine. Yeah, it's about 10 minutes.
Great. So, okay, so the idea is the following. The idea is that given a graph, like here, we can think of this graph neural network as learning two functions. One function is a message that each node would send to their neighbors as a function of their state. And the other function that they learn is a way for each node to combine all the messages that it receives. So in particular, and this is a picture from a tutorial by Juri Leskovic, and what they do, well, like the idea is that, so for instance, B receives messages from their neighbors A and C in the first layer, and then in the second layer, it sends a message to their neighbors B and A, etc. And so the information gets passed, gets disseminated in the graph by this mechanism. Another form of thinking about graph neural networks is by thinking of as a generalization of convolutional neural networks. So now, if you're familiar with convolutional neural networks, you take an image, you look at a subset of the pixels, and then like a piece of the image, and then you have a filter of a way to combine the different different pieces of the patch. So in these graph convolution networks, the idea is the same, but then your window is going to be as the neighbors of your node, and this is this formulation is very connected to the idea of the message passing neural networks, and it can be seen that they are equivalent in a certain way. Another different formulation on graph neural networks is to think about them as building like the composition of different layers, each of them satisfying the symmetries that we want to have in our function. So the typical case, or one case, one way of seeing it is like we can think that the input is say a tensor, and then then you go from one layer to the next layer. And so if you apply a permutation input, then you want that the output in that layer has the same permutation. And all the functions that have this property with respect to permutations and are linear form a linear space. And you can actually parameterize what is the, like you can actually compute what is the dimension of the space that the space of linear functions that satisfy that property. And maybe you can even parameterize them. Though the dimension of that space is very large, so that can only be done for like low order tensors, not for large order tensors. And with that, you can define a graph neural network as a composition of well, linear invariant layers, right? Or like equivariant layers. So you take an input that is in dimension, like you have like this, and this here you have like your entries, which is like, let's say a tensor, a K tensor in Rn, and then your next is like a K2 tensor, K3 tensor, etc. The output maybe is a real number or anything. These maps here are linear. And these linear maps, maybe you can do a linear map with a point-wise nonlinearity. And these linear maps that go from here to here and satisfy the symmetries, equivariance, you can parameterize them and you can just optimize in that space by finding a basis and parameterizing that. So that is only doable for very small values of K1 and K2 and Kn, like the order of the tensors. But it can be proven that if you construct a neural network in this form, then you can universally approximate every invariant and equivariant function satisfying those properties. So if you allow yourself to go to very high order tensors, in the same way that polynomials can approximate every function. Anyway, so if you want to consider other groups, not just the permutation group, then typically what people do is they consider, I think there's some noise. What they do is they consider the irreducible representations of the group, and then they build the building blocks of the network in this way. Okay, so I wanted to mention that something that I worked on is about how we can think about the approximation power of these neural networks. And in particular, there is this very nice work by Su and Moritz independently in 2019, where they characterize the expressive power of different graph neural networks in terms of their ability of solving the graph isomorphism problem. So in that case, they show, for instance, that this is equivalent to some graph isomorphism test, etc. And they can show that if you just do like simple message passing neural networks with no features in your nodes, then you cannot distinguish many graphs that cannot be distinguished by this Weisser-Ehrlichman test. In particular, you cannot distinguish graphs of these two forms that I have here, like the graphs that are regular and have the same degree. And you can use that idea of like understanding these graph neural networks as embeddings that maybe are not much different than some graph isomorphism tests, to think about the approximation of these the approximation power of these message passing neural networks. And something that we did was like we considered many classes of graph neural networks and wrote a hierarchy of how these graph neural networks compare in their expressive power. For instance, something that you can see is that this weight per element test is equivalent to like the simple linear program that you can write, and is equivalent to is less expressive than message passing, but other hierarchies are other graph neural networks are more expressive, etc. And in particular, you can also see that these message passing neural networks cannot be used to count substructures because it cannot, like if you think, can I write a message passing neural network that given a graph, it tells me how many triangles you have or how many hexagons you have? The answer is typically you can't. And that's because this message passing is very local. And so you're not able to identify where the message came from and are not able to identify complex structures like something that doesn't look like a star or something very simple. So the next question is like, okay, these message passing neural networks have very limited expressive power. Is that hopeless? And the answer is no. And the way you can think about it is by how people in signal processing think about these graph neural networks. Basically, what they think about is like, instead of thinking about like some embedding of my nodes of my graph, they think of the graph neural networks as a transformation that takes a signal on the graph and outputs the solution. So instead of just thinking about like what it would look like for like just the node features that I have, it's like what happens if I change the node features at every like consider different set of node features and see how the graph neural network embeds different set of node features. And that's what they discuss. And for instance, there's a very nice lecture series by Alejandro Ribeiro, who's also from Uruguay, by the way, and he explains how to use these graph convolutional network filters to understand many properties of graph neural networks, such as the expressive power and, well, in terms of spectral methods and transferability and generalization, etc. So I don't have much time for now, I think. So I went a little bit fast on the last part of the talk, but I just want to give you a summary to say, okay, graph neural networks can be seen in many ways as over-parameterized spectral methods, as message passing methods with limited expressive power, unless you do something smart with the node features. And you can think of them as a composition of many equivariant layers and equivariant maps for signals on graphs, which is the last part that I mentioned. So there are many things to, I think that this kind of gives a very short overview of many ways of seeing graph neural networks. There are many open research directions, actually, for many of these topics. And thank you so much for your attention. I have a few references more towards like my work, but there's a very nice survey, and also maybe I should have written a reference for Alejandro Ribeiro's lectures. So he has many online about graph neural networks from the signal processing point of view. Thank you so much. I'm sorry I went a few minutes over time.
Thank you, Soledad. So we have time for 1 or 2 questions. If you have a question, you can unmute yourself.
So there's a question in the chat by Dennis asking, what are the major differences between graph convolutional network and convolutional neural network? So GCN and CNN. So from my point of view, the major difference is that when you look at the graph neural networks, you are asking that the functions that you learn are equivariant or invariant with respect to the node permutations. so the relabeling of the nodes. So if you're given your graph as, say, an adjacency matrix with some features, then you don't want that the function depends on like the order that I give your nodes. You want to have something that if I change the order of the nodes, then the order of the output changes accordingly. And I think that's the major difference between these objects.
Any more questions?
Okay, thank you so much for inviting me. I hope this was useful and not very rushed. And yeah, I'll stick around for the social. If you have more questions, reach me there.
Thank you very much, Soledad. Please, everyone, let's thank our speaker. Virtual applause or noisy applause, whatever you prefer. Our next speaker is Professor and Entrepreneur Alvaro Soto. Alvaro received his PhD in computer science from Carnegie Mellon University in 2002, with specialization in cognitive robotics. Afterwards, he joined the Catholic University in Chile, where he is currently an associate professor. At the Catholic University, he leads the Artificial Intelligence Lab, a leading research group in Latin America with more than 50 members. Also, he is one of the co-founders of CPEDI, an AI-based company dedicated to creating robots for the retail industry that currently operates in several countries. His main research focuses on studying different aspects behind the creation of cognitive machines. Today, he will present Beyond Memory, coaching our AI models. Please join me in welcoming Professor Alvaro Soto.
Okay, so thank you very much for the invitation. It's a pleasure for me to be here and tell you about the activities that we do in our lab in Chile. So in this talk, I will tell you about that. I will tell you some of the activities that we do in Chile, and our group is called the IA Lab, or Artificial Intelligence Lab. At this point, it's composed mainly by 5 faculty professors, around 20 PhD students, and around 27 master students. So we cover different areas of AI, like cognitive robotics, vision and text processing, explainable AI, meta learning, knowledge representation, and different application areas. Well, I don't have the time to go about all the activities that we do in our lab, so I just pick up one example that is related to the title of my talk. This is Beyond Memory, coaching our learning models. And it's one of the ideas that we are pursuing in our lab, so that we provide you with an example of the kind of research that we perform in our lab. So there have been some papers recently talking about deep learning as a maybe doing some memorization, working mostly as an associative memory that is learning some correlations in the data. But that's powerful if you have a lot of data available to feed this memorization. But it also has some weaknesses, and there has been also some papers pointing out about some weaknesses of these techniques, such as being easily fooled by some spurious correlation, and also some limitation in the generalization capability when this generalization needs more semantic understanding or some systematicity to complete the task. So this is motivating us to try to see how we can really move this model from this memorization operation. And the way that I like to see this problem is related to an old story that is, I don't know if this story is true or not, but it's very known about Einstein. That someday a journalist in an interview asked Einstein to to see if he can explain the theory of relativity, but in simple terms, so everybody can understand. So Einstein said, okay, but before that, he asked the reporter to explain first to him how to fry an egg. You know? But Einstein added that when he explained about this frying an egg, he cannot assume that Einstein knows about what is an egg, what is a saucepan, what is oil, what is the fire, and so on. And I believe that this is very related to the way that we are teaching now our deep learning models, in the sense that we are asking sometimes to solve a task that needs really a very deep understanding of the semantic of the task or the semantic of the word. But we are not providing that much information to this learning process. No, we are just providing input-output relation in a supervised training modality. So this is very different of how humans start to grasp the world. No, we usually have a lot of information from the world that tells us what is the right representation to really encode some key information, some key semantics, some key causal relations that can provide better generalization. So this is one of the motivation that is pushing our research. So the question is how then we can provide this more semantic information to bias our learning models to learn more powerful internal representation. So this is what I mean by this going beyond memorization and going in the coaching more closely our learning models. And I will provide you today, I will show you today 2 examples of how we are pursuing this idea. So the first one is related to BQA. So BQA is the task of answering a visual question. For example, here you provide the model with a question in textual form. For example, what game are they playing? And then you provide the image and the model should provide the answer. In this case, is baseball. So the usual way that you can solve this problem, or you can try to solve this problem using deep learning, is that you have your image and then you create an embedding of this image using your favorite deep learning backbone, and you have the text, and you also use your favorite textual backbone, and then you create the embedding of the textual input, and then you combine both, and usually you solve this as a classification problems among the most repeated, more frequent answers in your training data. So what we did here is that we augment this model providing more supervision. So what is that supervision? We provide a supervision about the part of the image that the model should use to answer the question. For example, here we can provide information here in an auxiliary task, supervision about the area that is more relevant to answer the question. And to obtain this supervision, we find information from visual genome. So visual genome is a huge data set of visual data, and they have all these manually selected regions and with information about what is going on in the different regions of the images. So we create a system to automatically given a question and an image to select what are the regions that are most suitable to answer the question. So using that information, we provide supervision to complete the model in this way. And well, we tried that, and we had some very good results. We increased a little bit the state of the art in this task. But most important, we checked that the internal representation was more closely related to the real causes that should be considered to answer the question. For example, in this case, the question is, what color is inside the cat ears? And this is the region that a human used to answer the question. This is the region that an state-of-the-art model used to answer this question. And this is the region that our model used, where they put the attention to answer this question. So you can see that the internal representation is very related to the true reason or the true information to really answer this question. So also in a related work, increase this model, not provide information in the way of a knowledge base. We also use visual genome in this case to extract some triplet that encodes some relevant knowledge about the world. For example, that man wears shirts or man has hands, and we create then a knowledge base, and we then train a model like this. We have the image, we have the textual question, and now we have these triplets given by thousands of relations that we extract from the visual genome. So we create the embedding of the image, the text, and the knowledge base. We mix those embedding, and we are able to answer the question. For example, in this case, what is the man doing in this image? And the answer was surfing. But we are not only able to provide the answer, but we also create an explanation of this answer. So in this case, we use a model to, in this case, for example, provide a textual explanation because he's writing a wave in a software. And also we provide a visual explanation in the sense that we are able to highlight the areas where the model put attention to answer the question. And also we provide some attention in the knowledge base in the way that we can output what are the rules, the triplets that the model use mostly to answer this question. So what this is an example in the case what we did in this following this idea of coaching our learning model is in the semantic that we provide the model. Well, this is what you should consider to answer this question. So another example that I would like to share with you today is related to semantic robot navigation. This is in collaboration with Stanford University. So the idea is that you had a robot and you want the robot to do autonomous navigation in a real environment. So usually the way that people in robotics solve this problem is using a metric map. This could be a 2D metric map or a 3D, depending on the sensor that you had available. Now in this case, you had a 2D. So, but this is very different to the way humans solve this problem. We human, we don't have a very accurate metric information of the environment that we usually navigate. But we have some information that is most related to what I call here a topological map. For example, you have information that your environment maybe has some offices, and these offices are connected to corridors, and executing some behaviors, for example, going out of an office, you can get to the corridor, and so on. So using that vision about how human mix knowledge, what we did is that we first train our robot to execute this task. So we train a robot to do tasks such as turning left, turning right, corridor follow, find a door, going straight, and so on. And to do this training, we use a simulation. We had an environment. Actually, it was a photographic reconstruction of a real environment. And we use data, generate data from this environment to train this behavior, such as whether follow, or maybe turn to left, turn to right, and so on. So in this case, what we provide to our robot first is a set of tools, a set of abilities to solve the task. These abilities are given by these behaviors. And then we try to solve the task. Actually, we use also a graph neural network to the topological map of the environment, the graph neural network that we provide localization, which node of the topological map we are in. And we also have a navigational plan, what node we should traverse in order to go from an initial point to a goal position. And then when we try to execute this path, take care, giving control to these behaviors, that these previously learned behaviors to do the navigation. So these two examples show you this idea of how we can provide more training data. In the first case, providing a different training scheme. In this case, training part of the model before in a modular way, training this behavior can help us to using deep learning beyond this ability of just memorizing or just finding frequent correlation in our training data. And I believe it's a very fruitful path to continue doing progress and try to move our model to the next level.
Alvaro, you're fading off.
Sorry?
Your sound is fading off. It's a little bit hard to hear you.
Okay, so let me go on. Oh, now it's better?
Yes.
Okay, thank you for telling me. Okay, so now we'll tell you a little bit about some applications. So in the lab also, we want to move our technology to the real world, to real application. And I will tell you a little bit about the first one is application that we did in collaboration, in our participation, also with the Millennium Institute Foundational Research on Data. It's about perception of public spaces. So what we did here is first showed the humans different images, and we asked the humans to provide these labels. Like, for example, for these images, we asked the question, which place looks safer? And the human ordered this using these arrows. And then we asked questions not about the safety, but also about the wealthy, how boring, how depressing are the different images from the city. And then using these images, train as a fire, so you see the level of these attributes, like beautiful, boring, depressing, and so on. And the way that we collect these images was at the location of each of these images. So then, using the information of the localization and using the information of the classifier, we try to create a visualization of how these different attributes distribute across our city in Santiago, Chile. So this is the map of Santiago, and you can see here from blue less, yellow more, how different. For example, we can see here that according to the images, people consider that the beautiful part of the city are here. The more boring are here, and this is more depressing, or this is more wealthy, and so on. So this was an application of how the perception of public spaces, and now we are also trying to go further to try to see another attributes that are related to how people perceive their neighborhood, their environment. So this is a work in progress. But the main idea is that one. You can use this classifier and the geolocation to study, how the people perceive the cities. So we have very nice application. We also in our lab we had some startups. One of them IR related is City that is developing robotics for retail. So I will show you a video of
Cipedi es una empresa de inteligencia artificial. El objetivo es mejorar la ejecución en el retail. En un supermercado pueden haber cerca de 30.000, 40.000 distintos ítems, y que esté el inventario en la sala es una cosa que es una tarea titánica. Las tiendas pierden cientos de millones de dólares en el mundo en este problema.
Creo que todos hemos vivido la experiencia de llegar a la caja del supermercado y darnos cuenta de que un precio está incorrecto, ¿no? Y tener que esperar minutos y minutos para que se solucione el problema. que los precios están correctos, eso se evita. Lo mismo hemos tenido la frustración que llegamos a buscar un producto góndola y no está. Bueno, gracias al robot eso se ha disminuido casi a cero.
Bueno, that's CPD, what the robot doing in the store. For example, they create this panoramic shelf and is able to detect things like the price tag and then check if there is problem with the price tag. You can also detect the products in the shelf and detect situation, for example, of stock out, or some missing products and the products that are in wrong position, and so on. So at this point, CPD has been very successful. They have more than 50 people working in CPD. It has operations in Chile, Colombia, and USA, and today it's worth more than $30 million. Another case of a startup that came from our lab, or is related to our lab, is Noto. Noto, what they do is they produce different food vegetables and plants. So, for example, they produce nut milk, that is a milk that is made of vegetable, nut burger, that is some meat based on vegetable, not mayo. Mayo is ice cream. They had different products based on vegetables. So let's see a video.
Some say we are what we eat, but what if what we ate changed radically?
So what's this?
So this is actually nut milk.
What is this nut milk made out of?
Mushroom species, a couple of seeds over here. You're gonna see chia, you're gonna see linseed.
Using artificial intelligence and state-of-the-art technology, a Chilean food tech startup is making plant-based foods that replicate the taste, texture, and even smell of animal-based products by copying their molecular structure.
So that's NAFCO. Also at this point, NAFCO is getting very big. You know, they have more than 100 people working in the company at this point. It has operation in several countries, and today is worth more than $100 million. So it's a big company. Actually, it's one of the most successful startups from Chile. So these two examples also show the relevance that we can, or the impact that we can produce. We can even use this technology in our countries in Latin America. So to end my talk, I will just touch about research collaboration in LATAM. So unfortunately, at this point, we're not doing that well in research in AI. This is a graph that shows the evolution over the years of the research publications related to AI. And Latin America, unfortunately, is here is not really doing very well. It's just 2.7% of the papers. And actually, if you go to the statistics of relevant conference, such as ICLR or NIRIS or CTPR, we're doing even lower. Sometimes we don't even have the 1% of the papers in the conference. So there we had a challenge. And one thing that caught my attention is that if you go to the papers in this conference, for example, these are papers for this year, ICLR, you can see things like this, no? For example, in this paper, these people from Berkeley, from Stanford, from Carnegie Mellon. So these places are very far, but they are doing collaboration. So we had a paper, people from New York and from England. Here you had a paper from people in Texas and people in California. So they are doing a lot of collaboration. And this is not really strange cases. This is a norm. If you check the papers in each of these conferences, and ICLR and NIRIS, so you can see that there's a lot of collaboration. And I believe that in Latin America, we have a lot to do. It's a challenge, try to increase the collaboration between our university, our research groups, with exchanges of students and joint proposal, joint grant funding. So I believe this is a very important, and I would be glad to start collaboration on my invitation. If any of you want to start collaboration with our group, we are very open, very, very open to start collaboration with people in Latin America. No? I think we our collaboration in research. So that is what I have for today, and thank you very much for coming to this talk.
Thank you, Alvaro. It was a very interesting presentation. We would like to have questions now. We have time for, again, 2 questions. Anyone?
I have a question. So about the last part that you said, do you know if there exist any mechanisms to like encourage collaborations within Latin America?
Well, I mean, there's some collaboration in the sense that governments, universities, for example, now I'm exploring a collaboration with some universities that my local university has some special agreement. But I believe there is not much formal collaboration. I mean, for example, I don't see, at least in Chile, any request for proposal where we had to go like to universities from Latin America. We need more of those instruments, you know. And also, one thing that I think we really can improve is the collaboration in terms of exchange of students, you know, because that depends mostly on the funding that anyone has available, and I believe that is also a formula that works pretty well from the people in US. I see in US, I spent a sabbatical in 2017 in Stanford, and I see that the students, and they go to internship to different places, and there's a lot of exchange in terms of students. So that's, I think, a good way to increase this collaboration, and also collaboration with John Hopkins. I work with Rene Vidal, Rene maybe from John Hopkins.
Yeah, of course.
Yeah. So we had papers together. Actually, one of the papers that I showed today was with Rene.
So Uruguay has like a formal collaboration in math with France. They have an institute that is like France, Uruguay, and I would say that half of the PhDs in math in Uruguay did their PhD in France. So like the same thing, there's no reason why there shouldn't be something that is across
similar
Latin America.
In Latin America, yeah, that's. We I think we need to push that too. Is that we need to be more active. That is my message there. Sometimes we are waiting for somebody to do this, and maybe we are that somebody. We had that responsibility maybe to increase the collaboration in Latin America. So we are very, very happy that in our group we had some PhD students from Colombia and from Ecuador. And that, I think, also helps.
So I have a suggestion that in Europe, for example, the framework program for European projects is called, well, it was called Horizon 2020. You probably know about it. And the new one is called Horizon Europe, right? But to participate in these programs, you need to be an associated country. And I think a lot of Latin American countries are already associated. So it's just a matter of having connections with people in Europe that in order to formulate projects. So I think that door is quite open, but like people from Latin America don't use it that much.
Yeah, maybe LatinX can help us, start to providing information about the opportunities. That's a task for the people organizing this event. Maybe you can also be and play a role in this too.
All right, let's thank our speaker, Alvaro, Soto, once again.